Is there life on Mars? No, almost definitely not. But was there life on Mars? Well, we might be getting one step closer to that answer. An interesting side note here that I think is worth discussing as we maybe inch closer to an answer for that question is this. Elon Musk, however you feel about him, has been absolutely aiming towards Mars with SpaceX. He wants to get to Mars. I think it's incredible. And what he's probably going to do with the first journey to Mars that SpaceX makes is put on board one of these humanoid bots that he's been creating. And will that artificial intelligence be the first intelligence on Mars, or at least the first intelligence on Mars in a very long time? In an article titled Search for Life on Mars Takes Major Leap Forward, scientists detect longest organic molecules on planet to date, from BBC Sky at Night magazine, which is an incredible title that I had no idea existed. We get the following. In March 2025, so recent news here, NASA announced that a team of scientists had made an exciting discovery analyzing rock or a rock that had been pulverized for study by its Curiosity rover. These are the largest organic compounds on the red planet today. So why is this? Why is this important? Why is this necessary to find in our understanding towards what life on Mars will look like? Well, organic compounds are what are the constituent components to life. You don't have life without organic compounds. Organic compounds is in reference, to the best of my knowledge, towards carbon and, is it nitrogen? Carbon and nitrogen makes a compound organic. So, like, all sorts of things are organic compounds, but they are not life. So, not necessarily was there life on Mars, but without any sign of organic compounds, we have no reason to even ask the question. With organic compounds, the very grammar of the question makes so much more sense. The findings were published in the Proceedings of the National Academy of Sciences, led by Caroline Freyssinet, a specialist in astrochemistry and a researcher at the French National Center for Scientific Research. We spoke to Caroline to find more. Caroline, yes, very good choice to go with Caroline as opposed to Freyssinet. Why is this Mars discovery so exciting? We found large organic compound molecules composed of 10, 11, and 12 atoms of carbon. These long chain-shaped molecules, called alkanes, are very fragile. They're much more fragile than the ring-shaped or aromatic molecules made of carbon that we detected previously. What this shows is that these long chain molecules can be preserved over geological periods of time. Now, obviously, that is an incredibly interesting find, but the important thing is they were on Mars. You found organic compounds and long organic compounds on Mars. The longer the organic compound is that we can find, the more likely substantial types of life could have been on Mars. Substantial types of life that you can maybe find of which you can maybe find a fossil, things like that, not just bacteria, but actual things that were moving around on their own volition on the surface or underground or in the water of Mars. They were found on rocks that are 3.7 billion years old, which means they were deposited 3.7 billion years ago and preserved until today. So the reason you can tell that is because the molecules were in the rocks, not on the rocks, right? Or under the rocks. The rocks did not form on top of the molecules, they were embedded within it. This has huge implications for the search for life on Mars, because we believe that if life ever existed on Mars, it was around the same time that these molecules were deposited. We're going to get a little bit into that in a moment. How do these long-chain carbon molecules relate to life on Earth? We think the long-chain alkanes could come from long-chain fatty acids. We believe that on the surface of Mars, these fatty acids assemble themselves into vesicles, capsule-like structures. That's interesting because this might also be how life originated on Earth. So that is an interesting thing that I had not thought of until this article either. Finding the vestiges, vestige isn't the right term. Finding traces of what was life on Mars might tell us more about the origin of life on Earth. If life on Mars was preempted before it got to the stage where life on Earth is, it would also suggest, seemingly, that the specific conditions for life to spring up do not have to be all that particularly um, precise, right? Because you are getting life to spring up in that situation, it would suggest that you're getting life to spring up where it is not the easiest for life to be sustained. Now, obviously, there are conditions on Earth where this happens too, but I think one of the sort of weird things that people who are looking for life and people who are like this, I think this comes up in archaeology a lot too. They think that conditions have to be a specific way, otherwise, it just doesn't work. People could not have lived there on Earth at that time. It just doesn't work. It was too cold. People live awfully cold places today, right? So I think that this is one of those sort of scope problems for, and it plays into the scientific method, right? Because you want to be critical, you want to think critically of every theory that comes up, but I think sometimes the answer to whether or not something could have happened comes too fast, because the improbability compounds in the mind of the questioner. It's possible that they came from chemical processes independent of life, or there may be a biological explanation. Oh, we can't yet determine whether these organic molecules are formed from biotic or abiotic processes, right? It is possible that they come from chemical processes independent of life, or there may be a biological explanation. Is there some middle ground? Is the chemical process actually the place from which life might spring? So I think that's an in-between sort of answer. What evidence do we need to confirm these molecules have biological origins? Firstly, we would need to detect more molecules from the same family. We found molecules in 10, 11, and 12 carbon atoms. But we want to extend this to look for anywhere between 8 and 18 carbon molecules. The second thing is that on Earth, there is a significant difference in the abundance of molecules with even and odd numbers of carbon atoms. With just 3 types of molecules, it's hard to spot a trend. What's next for your team? There are many potential first steps, which is great. Or next steps, pardon me. In the short term, the remaining samples we have on Mars can still be tested once we developed new methods. In the medium term, there is the next mission to Mars, ExoMars, due to launch in 2028. It's due to dig 2 meters into Mars's surface and would have the capability of distinguishing between the biotic and abiotic origins of the molecules. Interesting how fast that is happening on the heels of this discovery. So I am familiar with Mars today, though I've never been. However, I am not familiar with Mars of 3.7 billion years ago. So I went ahead and asked ChatGPT to give me a little bit of an idea what Mars was like back then, and we'll go over this together. Here's a quick snapshot of Mars about 3.7 billion years ago, right at the Noachian Hesperian transition, what it was like. Much wetter, but cooling, drying. River valleys, deltas, craters, crater lakes, and perhaps a northern ocean existed earlier. By 3.7 billion years ago, they were fading from persistent to episodic. snow, ice melt after the impacts or volcanism. So, whatever it was that caused Mars to lose its atmosphere, this is when it was losing said atmosphere. Now, how long does it take from losing an atmosphere to the absolute desolation of a planet before? How long does that process take? My neighbor sounds like a spider in the wall. I'm not sure what's going on there. But the interesting thing about that is it could help us understand where to best look for remnants of what was life. How far down would you need to drill? How long does it take for a planet to accumulate the type of dust and debris that currently is all over Mars? Knowing that, knowing where, for example, that potential northern ocean was, will help to narrow down where the search for where life could have been. Thicker air. The atmosphere was far denser than today. Estimates range from tens to hundreds of millibars, possibly higher, enough to occasionally keep liquid water stable at the surface. No global magnetic shield. Mars's dynamo likely died earlier, 4.1 to 4.0 billion years ago. By 3.7, the planet lacked a global magnetosphere, so the solar wind was stripping the atmosphere, one driver of long-term drying. So this was a very hectic time for the red planet. And how long? Okay, so it is possible that the conditions on Mars, if there was life, were more suitable for steady life than evolution. That is one of the interesting things about a planet that is as varied as Earth, perhaps not the most varied planet, but as varied as Earth. Things can change slow enough on Earth from, for example, wet to dry, that organisms have the time and the forcing function to evolve. All of a sudden, if you are a fish who has extra stiff gills or something like that, wings, if you will, your evolution becomes more likely than the fish who has a very soft body composition. Because natural selection can allow your offspring to survive for generations. How fast can organisms how fast can an absolute change in the environment in total happen and still allow for evolution to occur? That is something else that we might get an answer or to which we might get a partial answer. Rocks and watery chemistry. Clay sulfate shift. Earlier Noachian waters made neutral pH clays. Phyllosilicates. Around 3.7 billion. Widespread volcanism and atmosphere loss push conditions more acidic and oxidizing, leaving sulfate evaporate deposits, the classic mineral pivot seen from orbit and rovers. Erosion and sediments. Active valley networks, fan delta deposits, lake bed mudstones. Many of the layered rocks rovers study today were laid down in this era or just before. Very, very interesting that is the snapshot we are getting of this planet. Volcanoes and impacts. Tharsis rising. Major volcanic provinces, e.g., Tharsis, were belching CO2, H2O, SO2, which briefly warmed the climate but also acidified water. So, this is a rapidly changing planet at this point in time. That's why it kind of strikes me that this might be pointing more heavily to the fact that perhaps there was life. If these organic compounds from such a dynamic time on the planet are still available, it suggests that they were multiple. There was a lot of this stuff. For there to have been a lot of this stuff, there would have been some reason for there to be a lot of this stuff. This was not a onesie twosie type thing. This was all over. The fact that we are finding it, and we have covered a very small surface of Mars, finding it and being able to study it, to me suggests that this is a much bigger deal than it would outright seem. Big hits still happen. The heavy tail of bombardment continued. Large impacts could create short-lived, warm, rainy intervals and outburst floods, carving the first big outflow channel. Climate in a sentence. Not a uniformly warm blue Mars, but a cold, arid world with intermittent warm, wet pulses, enough to carve rivers, fill lakes, and leave chemical fingerprints. Habitability outlook? Yes, plausible. Neutral pH lakes and groundwater just before or around this time would have been chemically friendly for microbes. Later acidic settings were harsher but not impossible. Preservation potential in clays and evaporites is high, hence sample return targets. So, just a very interesting snapshot of what Mars would have been at the time these compounds were created or at least preserved. And maybe the answer to whether or not there was at one point life on Mars is coming faster than we previously thought.